In the framework of the Q.DOT project, we implemented at IT Aveiro a laboratorial prototype of a DV quantum key distribution system. In this system, the information is exchanged between the transmitter and the receiver using single photons with information encoded in the polarization. Alice, the transmitter, randomly sends to Bob, so we have here Alice, that is the transmitter, and Alice is going to randomly send to Bob 4 polarization states from 2 non-orthogonal bases. So Alice is going to choose between the horizontal state, the vertical state, the right circular state, and the left circular state. So basically, Alice is going to generate single photons and is going to encode the information, this information in these single photons. These single photons are going to send to Bob. That is the receiver. Bob is going to detect these quantum states using two different bases, also chosen randomly. So basically, Bob is going to choose or the rectilinear basis or the circular basis. Therefore, Alice and Bob ends up with 2 sets of random keys that are only half correlated. From these raw keys, they run a quantum oblivious protocol in order to obtain instantiations of random OTs. These random OTs are subsequently used to implement a secure multi-party computation service to be used in vehicular networks. The major advantage of using quantum technology in this service is the attained security. Indeed, we achieve at the end a solution that is secure even in the presence of a quantum computer, and this is something that classical technology cannot provide nowadays. But now, Sarah is going to present to you more in detail our setup laboratorial or the implementation of this DV quantum key distribution system.
In the next minutes, I will briefly present to you the laboratory setup developed here at IT Aveiro in the context of the Q.DOT project. This is the physical layer, which is responsible for the generation of the quantum raw keys that are used to generate the quantum oblivious keys used in secure multi-party computation. The setup comprises the transmitter, known as Alice, and the receiver, known as Bob. At the transmitter, we have 2 optical signals being prepared. One is the reference signal that will be used to synchronize the transmitter with the receiver, and the quantum signal that will carry the state of polarization. These signals are modulated by 2 Mach-Zehnder modulators. The reference signal will have a width of 100 nanoseconds, and the quantum signal will have a width of 1 nanosecond. And the digital signals that will control the Mach-Zehders come from the FPGA board. After the FPGA board, we will have a filter to eliminate noise, which is that black box in the back. Then, after the filter, we will have a linear polarizer that will ensure that the polarization at the entrance of the electronic polarization controller is fixed. And the electronic polarization controller that we are using is a piezoelectric one. By applying voltages on the wave plates, it will squeeze the fiber. These voltages are applied by the Arduino board, by external DACs of this board. After the electronic polarization controller, we have a beam splitter that divides the signal. One part goes to the monitoring setup, which is this whole part here. There are 2 main branches. One that will be responsible to generate the linear states, or to determine the voltages for the linear states, and the other one for the circular states. After this, after the beam splitter, the signal is guided to a variable optical attenuator to attenuate the signal before it goes to the quantum channel. After the quantum channel, the signal is splitted at the receiver. Then it passes on to the electronic polarization controller, which is also a piezoelectric one, as at the transmitter, where the wave plates are again controlled by the external DACs of Arduino board. After this, the signal passes on to a polarization beam splitter, which is this box here in the back. And depending on this polarization, the photon is guided to the single photon detectors, which are these two boxes here. And if it was a horizontal polarization at the entrance of the beam splitter, it will go to one photon detector, and if it was the other polarization, it will go to the other one. Then the reference signal, after it is splitted, it will go to the photodiode, where it will be divided into 4 different trigger signals, 2 that go to the single photon detectors, the other one goes to the FPGA, and the other one to the Arduino board. The final result of this project is a fully functioning polarization encoding QPD system, where a random bit string is encoded using a random encoding basis at the transmitter, and at the receiver the polarization states are decoded, also using a random measurement basis. The system achieved a quantum bit error rate of 3.27% after 10 hours of measurements.